So I'm going to explain 3D flow simulation over a semispan wing. So I'm going to use the Naga 2412 file. So these are all the coordinate points x, y, z. That is three coordinates we have to import it. As it is 2D, third column is 0. So first you have to open the CATIA. That is, I'm going to import it through the CATIA. So you go to start mechanical design, part design. So not the product. You have to go to start mechanical design, part design. Then go to the Excel sheet. You go to view macros, this workbook, main, run, enter 3 for points, spline, loft, etc. and all. So it is imported. You can close this, and if you use fit all in tool, we can visualize the error file. So as it has the point and line, we cannot use it directly. I am going to extrude only this line, then I am going to copy paste it for the further design process. So I will take the same parallel plane, go to sketcher. Now using this project 3D element, so copy the line alone. So I copied the line, then exit the sketch, delete the imported points because already copied. I don't want that point etc. and all, which may create issue in later stages. Then so I copied from the sketcher only. So I am going to the sketcher using the same plane. Now paste it. So this is the error file extracted from that imported points, and then I can go for the desired length. For example, I am going to extend this for the 100 centimeter. As now it is just 1 mm. Maybe just 100 mm I will try. So 100 mm. If you want, you can fix this. Fix the error file profile. And this, because we made a duplicate one, so you have to delete the existing one. Okay, so this got deleted. So this is the error file imported, and then I'm going to pad it, maybe for the same 100 mm. Okay, or around 50 mm. So this wing alone, I'm going to import it in the ANSYS. Then I will create the domain, then mesh generation. Then I can see the flow over this finite wing. So I'm saving this. Semispan wing. Then I can close it. Then go to ANSYS workbench. So use the Fluent. Then right click, import the geometry from the desktop, semispan wing. Then use the design modeler to edit the imported geometry. So first step is generate, so that you can visualize the imported geometry. So this is the model. Then I am going to create the domain for the fluid region. So it is in the XY coordinate. So select the XY plane, and using this you have to create this new sketch. So this is a sketch 1. We are in modeling toolbar. We have to go to the sketching toolbar. So select the sketching now, so that here you have all the profile creating toolbars, then operation like modifying, then dimension constraint, all the things are there. For example, simplicity, I am going just a rectangular domain. Just randomly I am trying rectangular domain. And if you want to give the dimensions, then you have to click these dimensions. You can give horizontal, vertical, general, etc. and all. For example, select this length. You see it is coming here. You can give just a 0.5. Then if you want to give distance between this axis and the line, it is coming. Maybe I can give 0.25 or 0.2. Like that you can give the dimensions. So this line is maybe 1, and distance between this axis and this line is 0.25. Okay, like that you can change the dimension. Then generate, that is come to the model, generate. Okay, this is the first sketch. Now I am going to create another one small rectangle, so that I can create blocking, another one small domain where I can refine the mesh further to the minimum value. Same procedure, say take the same XY plan. In that plane, go for the new sketch. Now we have sketch 2. Again go to the sketching. Again same rectangular tool. This time one small rectangle. Here also using the dimensions you can give the value. For example, this one I will take 0.5, and this one I may take maybe 0.12, and from here to here 0.06, maybe from axis to this line. You can press escape if it is coming wrongly, or after that you can delete also. Okay, like that you can use some dimensions, which are the dimensions required. Again come to modeling, generate. Now I have 2 sketches. Then I am going to extrude this. So maybe first I will extrude the, okay, inner is selected, but if you want you can select the sketch 1 first, outer one. So sketch 1 is selected. In the side view you can see properly. See this much it is extended. Maximum we can take just twice the span. So here I am going to take maybe 0.2, sorry 0.3, twice the length I am taking. Generate. If you want in the view you can go for the wireframe. Then I can create another one small, another one blocking near the wing, also just behind it, to predict the flow separation, floor therefore etc. and all. So again same procedure. Go to extrude. This time select the sketch 2, apply. So you choose add frozen, okay, so that later there won't be any issues. Otherwise every time you are creating the material for each blocks, you go for the art frozen. And this time again go to the side view. So I am going to create from the tip to some small distance. That is, for example, 0.15 means I can give 0.16, so that the small box is just covering the wing. Here alone I will get the very fine meshes. Okay, so 0.16 or 0.175 or 1.7, like that, depends upon the model you can decide. Just I will go with this length. So now you generate. So this is the domain I created. First one bigger domain. Then there is a small blocking closer to the wing model alone. That is for the flow refinement further. So in all the extrude, better you use everywhere add frozen instead of adding the material. You can try add frozen. Okay, every extrusion I have tried the add frozen. Input also add frozen only everywhere. Okay, then so in the ANSYS, wherever there is a fluid, then there should be a solid material. Wherever there is a solid model, that material should be removed. So to remove that, I am going to use create boolean. Using this you can unite, subtract, intersect etc. and all. So I am going to use this intersect option. Okay, so if you expand you can see all 3 body, that is aerofoil, the bigger domain and the smaller blocking. So I am going to intersect this aerofoil with this bigger domain. Okay, these two I am going to choose it as a tool body. Okay, so that the aerofoil will be removed, intersected. Both will intersect means wing will be separated. Now preserve tool bodies. That means in this case domain will be there, wing model will be removed, but better I will go for S with a sliced. That means wing alone will be cut, but it will be kept, body will be preserved, but it will be cut, sliced from the domain. With that you just generate. You can remove also, sometimes it may show error, so better I am going for this sliced, sliced method. Now you see we sliced, okay, the aerofoil alone, then the smaller domain, then the bigger domain. Now I don't want this aerofoil, so here you cannot delete, instead you can do the suppress. So now what you have is the bigger domain with the cut for the aerofoil, you can see. Okay, so wherever there is a flow, then there is a solid, and wherever there is a solid model, material has to be removed. Okay, so here we removed, you can see. And this is another one, small solid. Okay, so just to refine the mesh near the model, I have given another one, small blocking. So this is the overall domain creation. Then you have to go for the boundary name assignment. For example, select the face here, so you can select the body, face, line, point, etc. and all. Select the face, and this face will be the inlet. So right click, go to the named selection. This will be the inlet. Generate. Then I can take these three side as the free slip wall or far field wall. So again, for these three slides, first I'll give maybe far field. So inlet, far field is given. Then maybe next outlet. Select the surface, select this surface, then right click. This is outlet. Okay. Then remaining is this side, which is the symmetry, because we are taking only semispan model. If you are taking full model, then there will be a wing in opposite side also. Okay, full span if you take opposite side, then domain also should be extended symmetrically on both sides. Then symmetry option will not be there. But here I am just taking the cut view, only one half of the wing I am taking. So this face should be the symmetry. So right click. I think as there are two blocking, there will be two face. If you want, you can select both one, and you can see this window. You can see the second smaller rectangle also. Both, if you want, you can select. Right click. Okay, so this one, then press Ctrl. Second one also, right click. You can see the named selection. Already I selected the named selection. So both faces are selected. Name will be the symmetry. This is short form I entered. So inlet, far field, outlet, symmetry I have done. Then I can go for the airfoil. So here is the airfoil. So one by one, if you want to select, you can go for this point selection, or as a whole model if you want to select, you can go for the box selection. So I will choose the surface with the box selection, choose the airfoil. What will happen? Four side face will be there, but this side is the symmetry, so I don't want this face. So now you go to the single point selection, select the face. I will unselect this face alone. Okay. You rotate. Okay, already it is not there, I think. So you will see, just right click, go for the named selection. Okay, only three faces are there. Okay. So upper surface, bottom lower surface. This is the tip side, and this side we removed the model, so there is no surface here. So three faces I selected. I am going to name that as the wing. So wing also generated. This is the wing model. Okay. So wing, then to domain, so inlet, far field, backside outlet, then this side symmetry, then wing alone. Okay, everything we created. Now it is ready for the mesh generation. So right click, go to edit. So here also first will be generate, so that we can see what is the default mesh generated. So to visualize that, you have to click on this mesh. So this is the default mesh generated on the to domain and the error file. Now we can define it. Okay, in the statistics you can see totally 1,58,000 elements are created. Now I am going to refine further. So I am going to use sizing, that is locally I am going to refine on the error file, also on the small blocking. Then I am going to give the face meshing for the model, so that I can convert triangular cells into a quadrilateral cells. Then I am going to give the inflation layer on the model, okay, so that we can predict the bound layer, everything properly. So first I will start with sizing, or maybe first face meshing I will give. I will convert on the model unstructured mesh to structured mesh. So here also you can rotate, zoom, pan, and now I want to select the surface. So select here. So first one unselect, second plane if you select, you see upper surface is selected. Then rotate bottom side, again same procedure, select the surface, select on this. Here also first that symmetry is selected, so select the second one, you see bottom surface is selected. Now we don't want the symmetry, unselect it, only the lower surface is selected. Like that, two surfaces I am selecting it, okay, upper and lower surface. Then generate, so we are converting unstructured mesh on the model to structured mesh. So if you want, you can change the view. So display, you can go for shared exterior, okay, wireframe you go, you can see it properly. So select the mesh every time if you want to visualize. You can see on the model, you can see the rectangular cells, okay, up to certain extent it is created. Then I am going for the sizing on the error file, also on the blocking. So sizing, here also if you want, you can select manually, or already we have given the naming. So instead of geometry selection, you can go for the named selection. So all the name we have given will be displayed here. I can select straight away the wing, okay, and now it is 0.05, maybe I will give 0.001, okay, some refined value I will give. Then again go to home and generate. You can see how much it is refined, okay, on the error file. Then I can refine on the small rectangular blocking also, same procedure, mesh, insert, sizing. Now I am not selecting the face, I am selecting the complete block, this small rectangular block, that is the second one. So second one I have selected, apply, Here maybe I will just give 0.05. Let's see how it comes. So you have to do the mesh study. These are all just the initial mesh. Based on the CLCD, further you have to refine it. So okay, there is no much variation. That means you can define a little bit. Maybe 0.02 will you. So on the aerofoil, even 0.001. First, let me check 0.01. Otherwise, I can reduce further also. A little bit, it is refined. You can reduce further also. That's okay. Just for the demo purpose, I am showing. And if you want, you can do the sizing for the outer blocking also. So maybe there I will give 0.1. Let's see how it comes. If you want, you can refine it further. Instead of 0.1, it can be 0.05. This can be 0.07. Okay, so on the aerofoil 0.001, on that internal element it is 0.007. Here it is 0.05 only. Let's see how it comes. So this much it is refined. You can see the element. Now it is 10 lakh. You can keep on refine, depends upon the computational facility available. Maybe I will just proceed with this just for the example only, because further I have to show you the inflation layer creation also. So for the inflation creation, right click, insert, go for the inflation. Actually you have to calculate the y plus. According to that you have to create this. So first I have to select on which block from aerofoil is removed. So from the outer domain only aerofoil got removed. So outer domain first you have to select, then the aerofoil you have to select. So maybe I will try okay, completely on the aerofoil you can try, or only on the upper and lower surface also you can try. Maybe I will try with the complete one. That is all upper surface, lower surface, tip surface. If you want to select, you can go for the named selection, then you can select the wing, so that there will be inflation layer on the top or on the bottom, also in the side. Or that side if you don't want to select, you have to go for the geometry selection. You can select only upper and lower, both way you can try. So maybe I will go for the complete around the aerofoil, everywhere I will try to create. So around the wing, maybe one 10 layer and a smooth transition, like that. This one I will take it. Now generate. So click on the mesh. Now you zoom, go to closer view. For the aerofoil you can see the inflation layers, 10 layers. It is created around the wing model, and it is now become 16 lakhs, because we created upper, lower, also in the sides also. Okay, so it's around 16 lakhs. Side if you cut, maybe just 1 or 2 lakhs may reduce. Okay, above, around the model everywhere we have created So with this 16 lakhs mesh, we will move further for the simulation. So every time whatever the changes you do, you have to generate, and at last you have to update. Okay, and you have to see the successfully imported what it's showing. There is a overlapping of geometry named selection, that is mistakenly I given some name here, I think. For example, mostly that symmetry where the error is coming, inlet is correct, far field is correct, outlet also only one it is correct, wing also just 3 it is correct, symmetry alone normally the error is coming. So right click the symmetry, maybe you select only one, two also can be selected, so both you select, then you generate, then update, and in that case you select only one symmetry, select only the bigger face. Okay, that alone you select and generate. Now you update. So two overlapping faces we have given symmetry, that's why error was coming. You select only one bigger face as a symmetry, so the mesh translation to Fluent was successful. That is, if you minimize, you should see the tick symbol, then only it is correct. Now you can go for the setup. So you can close this mesh. Now go to the setup. So Fluent is starting. Okay, already started. I noticed. Okay, so 3D by default is taking. If you select double precision, mostly for the proper study, we will go for the double precision. That is a 64-bit. More decimals will be taken in the iteration. If you want to select double precision, and if you have more number of cores, you can choose the multiple cores here. Otherwise, leave it with the one. So system will take the optimum core level. So my level just I am giving some 6 cores. I will take it now. Then start. So I had 8 cores, so I am selecting the 6 cores. If you have 4, 600, better you leave it. Software will allocate the cores whichever required. So low cores means don't change the number, you leave it with the one only. So the file is mesh is loading here. Okay. So I am going to do just some subsonic analysis only. So it will be just maybe 40 meter per second I am going to take. So flow can be assumed as incompressible, so you can go for the pressure based. And now I have taken just a 0 degree only. So up to 5 degree at least I can consider for the steady flow. Maybe after 5 degree I have to go for the transient time different study. So I am choosing for the pressure based due to incompressible. low angle of attack, I am choosing steady only. Then in the model, energy, if there is a temperature variation, you can choose, otherwise no need to disturb it. And viscous model, I will leave it to the basic k omega SST, or if you want, you can go for the transition SST also. So I am not changing anything in the model. Material also I am not changing. Then go to the boundary conditions. So inlet will be the velocity inlet. I have a flat surface only, I can leave it with a normal to boundary, or you can go for the magnitude direction also. For example, if you want to use some other velocity, then you see x velocity, x direction there is a flow, y direction it is vertical, x and y. So as it is 0 degree angle of attack, flow is aligned with x direction, we are giving 1 and the x, other under y and the 0. Instead, if there are some angle of attack, positive angle of attack, for example 5 degree, then instead of 1 you have to enter cos 5 degree in the x. Then instead of 0 in the y you have to enter sin 5 degree. Depends upon the angle, cos 5, sin 5, or cos 10, 5, 10, like that. That value you have to enter here. But now it is 0 degree, flow is aligned with the x direction. So 1 and 0 I am entering, and velocity I am taking as 40 meter per second. Temperature I am leaving with the standard only 288 or 300 by default value. This pressure far field also, if you have taken big, very big domain, you can keep it as a wall, or as it is very closer, instead of static wall, you make the static wall to the moving wall with the same 40 meter per second. Okay, so that there is no boundary layer growth, etc. and all. If it is static wall, definitely there will be a boundary layer growth. I will consider the wall also moving along with the flow direction with the 40 to avoid that boundary layer formation in this C section. So I am taking the moving wall for the far field, inlet, velocity inlet, outlet will be the same pressure outlet with the 0 Pascal, that is 1 atm. It is defined because why it is 0 here means in the operating condition already this 101325 is defined. Okay, so you should not enter another one time 101325 pressure. Okay, so already as it is defined, it should be 0. So software will take 0 plus the operating condition. So that means in the exit, flow is open to the atmospheric condition. So we are not changing in the outlet and all. Symmetry will be symmetry, wing will be a no slip static model. So what I changed is the inlet with the 40 meter per second, then far field walls as a moving wall. These two I have changed. Then reference value from the inlet I am going to calculate, and span of the wing is 0.1, and area is span into chord both side I have taken. I think a 0.15. I think span I have taken 0.15, chord I have taken 0.1. So it will be 0.015. Okay, 0.1 into 0.15. So you have to give proper length and area, then only you can find the forces acting on it properly. Then method I am not disturbing, I will leave it with the default value only. Then monitor residual, you can leave it with the 10 power minus 3, just software will check 3 decimals. Okay, and if it is matching, solution will be converged and it will be stopped. Normally for the research paper etc, we may go up to 10 power minus 6. Okay, but just for the demo I will leave it with the 10 power minus 3 only. Then I like to check how CLCD varied. For that, in the monitor I am going to see the CLCD value for every iteration, how it varies. So go to the new, another one new, go to force, drag on the wing. I want to see the drag coefficient. Okay, see drag coefficient is selected, wing is selected, and you can plot. Additionally, you can print in this console also, in the bottom also you can print that value. Maybe both I am giving. Same way, now create it for the lift on the wing, lift coefficient. I am changing the name as CL. I like to print it on the console also. So to value I am going to monitor. Additionally, if you want, you can check the Y plus also. You can go for the surface report, some facet average, then you can go for the wall flexes, turbulence, and wall Y plus on the aerofoil, that is on the wing. That is also, if you want, you can check. So I will give the name as Y plus for that. So Y plus also, if you want, you can check. Mostly you check CL, CD and CM moment we may use to check. Okay. So boundary condition, everything I defined. Monitor also, CL, CD I have to monitor, that I have defined. Now we can initialize. Already I have given proper input values, inlet, etc. and all. So I am going to do for the standard initialization. So from inlet, you just initialize, then run calculation. Just now I will run for 1000 iteration, but you have to go until the solution is converged or until your value is constant. These residuals should go down. It should not climb. That is, it should not climbing means diverging. It should not diverge. So the value should converge. Okay. So these lines also should come down only. And this how CL, CD, everything is varying. After certain iteration, this will become a flat line. So you can run up to solution is converged, or if you find for at least a few hundred iterations, if it is constant, you can stop. Either you can find what is the CLCD value. So here also it is printing. You see, this column is CL, this is CD. You can see how it is varying. Okay, so there is a variation only. Keep on, it is reducing, but this value will be almost constant after certain iteration. That time you can stop manually also. So after a few iterations you check, the values are almost constant because I have just taken the very less number of mesh and just 0 degree angle of attack. So this is the CL value, this is the CD value. So now you can stop. Okay. And in the result, you can check the contours. For example, contour you go. I can check the pressure maybe on the symmetrical wall, how it is there. So this is how pressure varied on that wing. Additionally, on the wing also you can see. Okay, on the wing. So here flow hits stagnation flow, then flow got accelerated, then here flow got separated. So this is how on the wing pressure varies. Same way you can see the velocity also. So this is how velocity variation happen. In the symmetry, if you see, it will be clear. Okay. So you have to further refine it. Just for sample, I have gone for some medium refinement. And you can check turbulent intensity or kinetic energy also. Like that, many property you can check it. Okay. So this one, if you want, you can adjust the size, the precision. If you want, you can keep it in the same way. Otherwise, you can go for the floating, maybe with the 2 precision. Okay, so you can adjust the properties here of this color map. You can increase the size also if you want. And to save this, just right click, or there is a camera button here. Camera button with a white background. It can be with a JPG image. Like that, you can preview and save this file. Okay, that's how you will save all the contour. Additionally, if you want, you can see the plots also. In the plot, for example, XY plot, I will check the static pressure, or you will go for the pressure coefficient CP, how it varied along the wing. That's how it varied along the wing. Then the left hand drag value from here itself, you can take it from this value. Okay, that is 0.1072 is the CL, then 0.0185 is the CD, or just the value. If you want to check it in the result section also, you can do it. So you have to go to this report. Okay, if you expand the report, there is a forces. So on the wing, you find the force along the x direction first. You see total CD is 0.018. Okay, so this is the pressure, this is the drag value in terms of Newton. This is the coefficient of drag. Okay, due to the pressure, due to the viscous, the total drag. This is the pressure coefficient, viscous coefficient, total CD. And you can little increase. Then if you want to find the y direction force, here you put 0, here you put y, that is 1 for the y. Now if you print, it will give you the CL, 0.1072 is the CL. See, previously CD is 0.018, now CL is 0.17. So this is the force due to the pressure, force due to viscous, total lift force in terms of Newton, 1.57 Newton. Actually, by changing this number, you can change lift, drag, etc. and all. Or every time, just before you see, this is the forces: x direction CD, y direction CL, z direction side force, like that. Here also you can see. That is any one direction CL or CD. Just if you check before that itself, that value will be available. So this is how you will check the CL CD. If it is steady, if it is unsteady, you will go for the FFT, time transition. If you do, this CLCD plot will not be a straight line, it will be a fluctuating line. Then maybe from certain portion, I will go for the FFT method. So that's it. So this way. So I have taken semispan. Same thing, you just go for the there is a 3D flow over the semispan wing. And if you want, you can make it as a 2.5D simulation also. That is the domain, whatever you created. For example, here, if you display, so the domain, I have given just twice the span length in the side. Okay, instead you give the same span length domain. If you create, it will be like a wind tunnel model, infinite wing attached in the wind tunnel, both sides is attached to the wall. That with that you can simulate for the 2.5D also. Like that you can change the domain. Yeah, that's it.